Alright, you guys, we're in video 11-4B and we're just talking about the final couple of shortcuts for proving two triangles are similar. And these are SSS and SAS. And if you recall from congruence, of course, S stands for our pairs of sides. And remember that the order matters when you see the letters SAS because we are talking about specifically an included angle, okay? So just mark these in your book and we're going to talk about how to use them on the next page. Alright, you guys, I'm on page 615 right now and we're going to work through example 2's part A and part B here. So, example 3's part A and part B. Example 3, we are asked to determine whether the two given triangles in this diagram are similar, and we are asked to justify our answer. So I don't know about you, but what I can see is an angle that's marked congruent in each triangle, and it looks like I do have the full side lengths of the two sides that include that angle. So let's read through here. It says you are given two pairs of corresponding side lengths and one pair of congruent corresponding angles. So we're going to try using SAS. Notice we're looking at this idea of we think SAS is going to work, but we must confirm. Let's write that down. Must confirm what we think is going to work. Okay? We can try it, but we need to actually prove it. So obviously we already know that the angles are congruent, so the only thing left for us to verify out of SAS are the two S's, okay? So that's where we use our proportions of corresponding sides. So our proportion that is set up here, or at least our ratios of sides to begin with, are MN to MR. MN is the shortest side of the triangle. MR is the shortest side of the bottom triangle. So notice what our ratio is so that we can be consistent here is that we are doing top triangle pieces and bottom triangle pieces. Bottom is the denominator. Top parts of the triangle are staying in the numerator. And we have 4 to 6, which we are going to simplify to 2/3. So the question is, are we able to get that same ratio of sides for a different pair of sides, the other pair of sides that includes the angle? So we've already taken care of the shorter sides of the included angle. Now we want to go with the longer sides, and again we still want to go top to bottom. So the top triangle has a longer side here. If we take a look at it, the top triangle has a longer side of the length of MP. Okay, that's the longer side of the included angle. And then the longer side of the bottom triangle is all the way from M to Q. So we're going to take 8 and 4 and we're going to add those together and we get 12 for that denominator. And then we're going to go ahead and simplify that fraction also down to 2/3. So because the ratios are the same for both pairs of corresponding sides, then we can say yes, they are similar by side angle side. But notice we had to actually verify the math for the two S's of our shortcut. Let's look at part B. In part B, we are given 3 sides on both triangles, and so we think that we should be able to try using the side triangle similarity theorem. 3 pairs of corresponding side lengths, and we don't have any congruent angles, so that's why you don't see any A's in our shortcut label, just sides. So we have to do 3 ratios of corresponding sides, and it looks to me, as they've started us off here, that we're doing LM to GH. So that's going to be the LM and GH, you guys, are my medium length sides. And notice that the ratio we've started off with going from the right triangle's segment pieces divided by the left triangle segment pieces. So as we're checking all these ratios, we want to make sure that we're keeping numerator and denominator consistent. So LM to GH, those are the medium sides, so that's 12 over 8. And that does simplify down to 3/2, just so that we can compare. MN is our large side, and MN is going to correspond to the large side of the left triangle, which is JH. So MN is 15, and JH is 10, and that also simplifies to 3/2. The only final ratio we need to check is of the smallest sides of each triangle. Again, we're starting with the right-hand side. So the numerator's right-hand side length, we're looking for LN, and the denominator's left-hand shortest side length is JG, which is 6 over 4, and that also simplifies down to 3/2. So looking at the all simplified versions of our side ratios, they are all the same, and therefore we can go ahead and write in and complete the similarity statement. Make sure that you're putting it in corresponding order. So I'm going to choose LMN for my first 3 letters. L is going to be the vertex that is across from the longest side. So the vertex across from the longest side in the left triangle is G. M is the one across from the shortest side. That corresponds to H. And finally, we have, of course, our J left over. And why are we allowed to say that? That is by the side-side-side triangle similarity theorem. So on the next page, just a couple of turns. I would like for you guys to check in on numbers 10 and 11 and make sure that you are justifying your answer by actually showing the ratios of any side lengths that you think might contribute to our 2 possible similarity shortcuts. And also don't forget, from the first video we had angle-angle similarity there as well. We'll see you guys tomorrow.